Hello and welcome to Empowered Learning. This video will go through several examples of how to solve logarithmic and exponential equations. If you're not familiar with the basic logarithm properties, then I suggest that you watch that particular video first before you watch this one, as we'll need those particular skills to be able to solve these equations. So let's go ahead and get started. So we'll start off with some ones that are relatively easy. We'll start with this first one here. Now, for this particular equation, for most of you that are familiar with your logarithmic properties, you probably already know the answer to this. And the reason that I'm saying that is because we have a logarithmic property that says log of any base of 1 is always equal to 0. And the reason we know this is because since the logarithm is just the inverse of the, I'll put it another way, it's the fancy way of saying the exponent for an exponential function. Thus, a logarithm is an inverse of an exponential function. We could rewrite this as a raised to the 0, which is equal to 1. So here we know right offhand that the answer to this is 0. If we wanted to form this into an exponential equation, we would just say 2 raised to the y is equal to 1. And so by the definition of a logarithm, we can convert that back to an exponential equation. And of course, 1 can be written as 2 raised to the 0. And of course, we have a exponential equation property that says if we have two exponential numbers or expressions that are equal to each other, and if the bases are the same, then that also means that the exponents must be the same. Okay? So whether we remember the properties here or if we go through the actual process, we'll see that we still get the answer of y equals 0. So let's move on to example number 2. So for example number 2, we really do want to convert this from a logarithm or logarithmic equation to an exponential one. So how we would do that is just say 1/3 raised to the y is equal to 9. And again, just to refresh you, just in case you don't remember this, I am using the definition of a logarithm, which is a lot of times quoted like this. And so here I'm doing a raised to the y is equal to x to convert from a logarithmic equation to an exponential. And so remembering this also saves you from not having to learn, well, you should still learn them, but not needing to use all of those logarithmic properties that you learn whenever you do this. You don't have to hold on to them as much because you can do this direct translation here. So anyway, my point is that now we can convert this to 1/3 raised to the y, which is equal to 9. And so now that we have this, we also note here that we could take 1/3 and we could rewrite it as 3 raised to the -1. And of course, now we have 1/3 written as an exponential number of base 3, and we know that 9 now is 3 squared. So now we see that we could use something similar to this example up here if we can somehow figure out what all this is. Now, of course, from our exponential rules, we know that 3 raised to the -1, all that raised to the y is just a 3 raised to the -y. And thus, now again, we have an equation where we have two exponential numbers or expressions that are equal to each other. The bases are the same, so therefore the exponents must be the same. And if we multiply both sides by -1, then that gives us that y is equal to -2. And that's what will satisfy that equation. Now, what this is actually saying here, and I'll go ahead and write it out, is that if we took 1/3 and raised it to the power of -2, that would equal 9. Or put another way, -2 is the exponent for the exponential function that has a base of 1/3 and its result is 9. So whenever we read logarithms, we're actually just looking at a fancy way of expressing the exponent of an exponential function. Okay? And we're literally asking this question here whenever we have a logarithm. And I'll just put it in the context of this problem again. This is literally what we were asking. Hey, if I have an exponential number that has a base of 1/3 and a result of 9, what is the exponent? That is what this equation is essentially asking. Okay. All right, so let's move on to the next example. So for this example, the first thing that we want to do, since we have this 1/2 that is being multiplied times log base 3 of x, there's two ways we could handle this. One way is to take the 1/2 and put it back here via our logarithmic properties as an exponent. The second thing that we could do is we could just multiply both sides by 2. And so to make life easy, I'm going to first multiply both sides by 2. But I am going to come back and do it the other way just so that you see how that works. So if I multiply both sides of this equation by 2, then of course this would just give me 2 times 1/2 is 1. So I just have log base 3 of x is equal to 4. Okay? And then from here, I see that my variable is trapped inside of the logarithmic function, so we can use the definition of a logarithm here. So we would just say 3 raised to the power of 4 is equal to x. And of course, from here, we know that 3 raised to the 4th power is just 81. And so that is our answer here, 81. Now, if we went about this the other way I was proposing the first time, then we could use the property that allows us to take this number and put it back in the exponent. And if we did it that way, we would have log base 3 of x raised to the 1/2, which is equal to 2. And then from there, what we could do is we could say, okay, 3 raised to the 2 is equal to x to the 1/2. So 3 raised to the 2 is equal to x to the 1/2. And from here, we understand that x raised to the 1/2 is the same thing as square root of x. So you could convert it to square root of x, or you could leave it in its fractional exponent form. But at any rate, from here, we know that 3 squared is 9. And so now we can raise both sides to the power of 2. And on the left side, we have 81. And on the right side, we know that we can multiply the exponents together. And we would just have x raised to the 1, which is just x. And so we see again that our answer is 81, no matter how we try to do it. All right, let's move on to example number 4. For number 4, the easiest thing for us to do here is to first divide both sides by 2. And by doing that, we now just get natural log of e raised to the negative 2x equals 4. And so if you note here, natural log is the same thing as log base e. Now I'm going to explicitly write this out so that you would remember corresponding property. Anytime we have log base a of the same number raised to the power of x, we know that we just get whatever's in the exponent. So looking at this, we see that the bases are the same, so whatever is in the exponent is what all this has to equal. So in this case, since negative 2x is in the exponent, that's what the result of all this is, and that equals 4, and thus to get x, all we need to do is just divide both sides by negative 2. And we see that we have x equals -2. Moving on to the next example, we see that we have e raised to the -2x equals 1/3. And so for this example, there's two primary ways we could do this. The first way that we could go about doing it is we can take the natural log of both sides. If we do that, then we will have natural log of e raised to the 2x equals natural log of 1/3. And so here, again, noting that natural log is the same as log base e of e raised to the -2x, we know that all of that could just equal to 2x. But here I'm going to do something a little different just to showcase another property. So another property that we know is that anytime we have log of any base, and what we have on the inside of the logarithm function is something of a different base raised to a power, we can rewrite that this way, meaning that we can basically take that value and put it out on the outside and multiply. And so that's the property that I am going to use here. So if I do that, then I'm going to take all this and I'm going to pull it out. And if I do that, now I have -2x times natural log of e. Let's clean that up there. Natural log of e equals natural log of 1/3. Okay. And so then from that point, we note that natural log of e is just equal to 1, because natural log of e is the same thing as log base e of e. And anytime we have log of some base evaluated at its base, we know that that's always equal to 1, no matter what the base is. So now here we just have a -2x, which is equal to natural log of 1/3. And here, what we could do is divide both sides by a -2. And of course, most people from this point would actually go in and put this into your calculator to get the answer for that. We could simplify a little further, and I am going to do that. But in general, if we wanted to stop here, this would approximately be equal to 0.5493. Okay. Now, if we wanted to keep on going, here we note that natural log of 1/3 is the same as natural log of 1 minus natural log of 3, all that divided by 2. And natural log of 1 is going to be 0, because log of any base evaluated at 1 is 0. And so now from here, you see that we have negative natural log of 3 divided by -2, and thus why you see that our answer up here was positive. And so natural log of 3 divided by 2 would be the exact answer. But again, if you plug that into your calculator and do it, you'll see that you'll get the same thing as we got right here. Okay? So that is one way of doing this particular problem. So what I'm going to do now is erase this and show you the shorter way of doing it by using the definition of a logarithm. All right, so doing this problem again, another way that we could approach this is by using the definition of a logarithm here. And I'll go ahead and rewrite that. And by using this, we realize that e is our base. We realize that -2x is our exponent, which is the y right here. And e is our base, which is the a. And our x here would be the 1/3. So rewriting this, we see that -2x would be log base e of 1/3. Or put another way, -2x is equal to natural log of 1/3. And now you see that we have the exact same thing that we had before, but less steps. So of course now we could say this is natural log of 1 minus natural log of 3 by using our logarithmic properties there. Natural log of 1 is 0, and thus x would be natural log of 3 divided by natural log of 2, because of course a negative divided by a negative, when we divide by a negative 2, would be positive. And of course again, this would approximately equal 0.5493. Okay. Moving on to example 6 now. So for this example, we note that we're using the logarithmic property that says that, hey, if I have log of some base evaluated at something and log of the same base evaluated at another something where the bases are equal, then if the bases are the same, then what is on the inside of the logarithms must be the same. So here we know that all this just means it's just square root of x plus 2 has to equal 8. And thus, in doing this, since we know that whatever value that we end up with for square root of x plus 2 has to always be positive, we can square both sides and know that we're going to get a non-negative answer, and thus just write x plus 2 here versus absolute value of x plus 2. And of course that would give us 64, and then we subtract 2 from both sides and we see that our answer is 62. In the next example, we will take this equation here and solve for x. And if you notice, our x's are on the inside of our natural log functions. So at some point, we're going to have to use the definition of a logarithm to free these variables so that we can actually solve for it. So the first thing that we notice here is that we have natural log of something minus natural log of something else. So we could rewrite this as natural log of x plus 1 divided by x all over 2. And here at this point, there's a couple of different ways we can do this. Probably the more intuitive way to do it would be to now say that this is log base e of x plus 1 over x equals that. And then from here, we use the definition of a logarithm to say e raised to the 2 is equal to everything that's on the inside of the logarithm. So here we'll say e raised to the 2 is equal to x plus 1 over x. And so now, since we have a fraction on the right side of this equation, we can make this a fraction on the left, and now treat this as a proportion. And the quick and dirty way of solving proportions is to cross multiply. So we'll do some cross multiplication here. And then from that point, since we need to solve for x, we need to have everything with x on one side. So we're going to subtract both sides by x here. And then from this point, I'm going to come up here for a second, and we're going to factor out the x out of both terms on the left side. And of course, that leaves me e squared in the first term and just 1 in the second term. Of course, because here this is understood to be a 1 right there. So I wanted to mention that just in case we may have forgotten that. And so now from here, e squared minus 1 is just a constant. It's an irrational number. It is ugly, but yet and still is still a constant. So now to solve for x, we just divide both sides by e squared minus 1. And so x is just 1 over e squared minus 1. And that is the exact answer. Okay? If you're asked to give a decimal approximation of this, then I'll go ahead and calculate that now. So that should end up to be about 0.1565. Okay. So if you're looking for a decimal approximation of this. Okay. All right. So the other thing that I wanted to point out here is that if at this point, if I wanted to do something different, here I could use another property, and this property entails using the fact that if we have a raised to the log base a of x, that would just be equal to what's inside the logarithm. In using that, what we could do here is I could use, let's say, 2 as a base for both the left and right side there. So if I did that, this would be 2 natural log of x plus 1 over x equals 2 raised to the 2. And so in doing that, I know that on the left side, this would just simplify to x plus 1 over x. And over here, this would simplify to 4. Okay. And so probably an easier way to do that. Yeah, let me switch that. Instead of using the base 2, I can use base e, and this will turn out to be a little better. So let me erase that right quick. Yeah, because I could do that, but that's going to make life. I can't do that because the base here has to match there. So these bases here have to match, and 2 doesn't match that. So I have to change that. So here, if I do base e here and base e here, then the implied base for natural log and the base here matches. So that actually makes more sense now. And so now, of course, that would be e squared, and now we have the same exact thing that we had at this point in our problem. And of course, we can go from there and use cross multiplication because we have a proportion there to be able to solve it. All right, so moving on. So example 8. For this one, again, we could take this 1/2 and put it back in the exponent of x here, and take this 2, put it back in the exponent of the 2 there. However, I am not going to do that. I'm first going to multiply both sides of the equation by 2. And by doing that, that will prevent me from having to even deal with that sort of thing on one side of the equation. So I'm just going to multiply by 2 here. And of course, 2 times 1/2 is just log base 3 of x. And on this side, this would be 4 log base 3 of 2. And so now I can take this 4 that I have right here and stuff it back as the exponent for that. And so this would be log base 3 of 2 raised to the 4. And this will be log base 3 of x. And so now what we have on the inside has to be the same because we have 2 logs that are equal to each other of the same base. So therefore, x has to be 2 raised to the 4, which is 16. So x is equal to 16. For example 9, this one is pretty easy to do. So the best thing for us to do in this case is just to divide both sides by 2. And if we do that, this will be e to the x is equal to 7. And then from here, the easiest way to solve this is to use the definition of a logarithm. And if that is the case, then what we're trying to model here is what we see from this. And so now, using the definition of a logarithm, we see that this x is in the exponent, which is the same thing here, which is what y would be there. So if we switch this around, this would be x equals log of, and the base is e of 7, and of course log base e is just natural log of 7. So our answer here would be exactly natural log of 7. Now, if we wanted to do the same problem, but do it by taking the log of both sides, then it will look as follows. And I'm going to go ahead and erase some of this first. Let's see if I can get rid of this. All right, so now if we came from this point, and let's say we wanted to do the log of both sides, I'm going to take the natural log of both sides to make it a little better, but I could still do log base 10 if I wanted. So here, natural log of e raised to the x is just x, because again, natural log is same as log base e, and then you have e raised to the x. Of course, all that's just x. And then, of course, this ends up being natural log of 7. So no matter how you go, you still end up with the same answer there. For example, number 10, sort of the same thing. In this case, since we have a base of 10, the best thing to do, if we're going to take the log of both sides, is take log base 10, which is just log written by itself. Of course, in this case here, we see that log base 10 of x is just x. And the answer to this is just log base 10 of 14. Okay. Of course, we could have also just used the definition of a logarithm and just said that here, since the exponent is just a fancy way, logarithm is a fancy way of expressing the exponent, we could have said x is equal to log base 10 of 14. And of course, log is the same as log base 10, because since it's the most common base used, we do not write it because it's assumed to be 10 there. And so we still end up having log of 14, log base 10 of 14 as our answer. Okay. Now for number 11, as you see, it's very similar to number 10, but what's different about it is this. Here, in order for us to be able to do it like how we've done here, we would have to do log base 3 of both sides. Okay, and of course, people are not normally used to working in log base 3, but I'm going to do it to show you how we could use the change of base rule to get a similar answer if we did not work in log base 3. So log base 3 of 3 raised to the x is just x. And of course, our answer here would be just log base 3 of 14. Now, if you do not have the capability of evaluating log base 3 of something on your calculator, you could use the change of base rule. And the change of base rule says we can change from any one base, which in this case will be 3, to any other base. And I'm going to change to base 10 by saying log of whatever's inside here goes on top, divided by log of whatever the base is goes on bottom. And so this is an equivalent way of expressing this answer here. Now, if I wanted to do this strictly by taking the log base 10 of both sides, this is how it would look. And I'm going to kind of section off some room here. So this would be 3 raised to the x equals 14. And then we would say log of 3 raised to the x. That didn't come out too pretty. Let's try one more time here. So raised to the x equals log of 14. And so now from here, we would have to use a property that lets me take this x and pull it on the outside. So I would have this now, and that would be log of 14. So now we would divide both sides by log base 10 of 3. And of course, x would just be equal to log base 14 over log, log base 10 of 14 over log base 10 of 3. And you see how we get the same answer there. Okay, so now for our final example, you see that for this equation, we have two exponential expressions that are equal to each other, but they are of different base. Since they are of different base, we must take the log of both sides. And so what I'm going to do is take the natural logarithm of both sides, which means I will do ln of all this equals ln of all that. And by doing that, whatever is in the exponent, I am allowed to pull out. So this will be 1 minus 2x, all that times natural log of 3. And let's try to write that a little neater. Equals, take this x and pull that out as well, be x times natural log of 4. And so now our goal here is to solve for x. So we're going to distribute our natural log of 3 into both terms here. So we have natural log of 3 minus 2 times natural log of 3, all that times x. And I'm putting the 2 and the natural log of 3 together because both of them are just numbers, so I'm multiplying. And then here, this is natural log of 4 times x. So here I see that this term and this term have x's in it, so I'm going to take this term here and add it to both sides so that I can have x's all on the right side. So if I do that, then I have natural log of 4 plus 2 times natural log of 3. And of course, both of these have terms of x with it. Okay? At this point, I'm going to factor out the x out of both terms and just rewrite natural log of 3. And then at this point, I could just divide both sides by natural log of 4 plus 2 natural log of 3, but I'm going to simplify it some more, only because I've noticed that the more logarithms we have to punch into the calculator, the more susceptible you are to possibly getting the wrong answer if you have to approximate these answers to some decimals. So what I'm going to do is simplify this. So here I know that I can take this 2 and move it back in the exponent of the 3 there, and that would be 3 raised to the 2, and all of that multiplied by x. And of course, we know that 3 squared is 9. And we also know that we have log base e of 4 plus log base e of 9. So that together will combine to eventually be log base e of 36. And we'll go ahead and say, hey, all that is just 36. And so now from here, I'm going to go ahead and come back up here. We know that we have log base, natural log of 3 equals natural log of 36 times x. And so now we can just divide both sides by natural log of 36. And before you even think about it, I know that 3 goes into 36 12 times, but we cannot reduce this here, okay? We are not allowed to say 3 goes into 3 once and 3 goes into 36 12 times. And the reason is that, of course, 36 is inside the logarithm function. So there's it's trapped inside of it. So we can't do any reducing here. This is not natural log times 3 and natural log times 36. It's natural log of 3 and natural log of 36. So we have to just keep it how we have it, okay? Another thing that I want to make sure that you don't make this mistake. Some people will get here and think that the end of this is just natural log of 3 minus natural log of 36. That is not true as well. The property does not mention anything for log of something divided by log of something else. That actual property is this. And so if you notice, the quotient has to be on the inside of a logarithm. You can't have a quotient of 2 logarithms and expect to simplify that or rewrite it in another way. Okay, so here we would just have to leave the answer as natural log of 3 divided by natural log of 36 if we wanted the exact answer, or if we needed a decimal approximation, this is where we would put this in our calculators and just type in natural log of 3 divided by natural log of 36. And we would get approximately 0.3066 as our answer there. Okay, and so this would be the answer. So this is the final example, and this concludes this video on examples of solving exponentials and logarithmic equations.